Hello, everyone. Thank you for attending this webinar. I will give like 1 more minute to see if more people are joining, and then we can start. So we're 21 attendees so far. I think we can already kick off this event. So hi again, everyone. My name is Amel Barish. I am Senior Project Manager at the Georg Geothermal Research Cluster, and I have the pleasure to host you today for the first Compass webinar. It is the first of a series that we will undertake in this year. This is an initiative from the consortium to start engaging basically with the geothermal community. So yeah, so we will open with a full Compass panel today. But before that, before introducing them, I will talk a little bit about the structure of the event. So the program will be as follows. So I will start introducing the project a bit as a whole, and our speakers, and then we will have two sessions. The first will be focused on the engineering aspects of Compass in terms of the solutions we're developing, the challenges that are out there and are lingering, and the second session will be about sustainability aspects and social acceptance. And we will end with a Q&A session where you can ask all the questions you have in mind. So a little bit about Compass. This is an engineering focused project that has an ambition basically to tackle challenges in terms of the geothermal well designs in superhot geothermal contexts, with a vision to basically support unlocking the huge potential that near-magmatic geothermal resources are holding. And practically speaking, we have been in the past few years developing and currently testing and verifying improved and innovative drilling and completion technologies in order to basically increase the chances for high enthalpy geothermal wells to be economically viable, and also supporting the environmental aspects around geothermal drilling in terms of reducing basically the footprint of wells and drilling, and basically the overall also like environmental and social impact of such developments. Compass is a consortium of 10 partners from Iceland, basically, as the coordinator, Norway, UK, Italy, France, the Netherlands, and the coordinator in Iceland is On Power, supported by Reykjavik Energy. The budget is around a bit more than 4.1 million euros, and this is a grant from the Horizon Europe. So moving on to our speakers, we have 4 speakers from the Compass Consortium from 4 different partners. Our first speaker is Hugh Huang, who is basically a senior scientist at SINTEF in Norway, and he is an expert in geothermal energy, thermal energy storage. His expertise also includes geothermal well design, high temperature applications, and materials integrity, on which his talk will be about today. And then moving on to Tommaso Maccio, who is a project engineer at TWI and is a specialist in laser additive manufacturing. His expertise includes powder bed fusion, directed energy deposition, and extreme high-speed laser application, also known as EHLA technologies. And his talk will be focused on that. So Tom has been leading the first project actually in the UK developing such technologies, which led to also the largest cell being developed in Yorkshire in the UK as a consequence of that. And then we have Arna Paulsdottir, who is head of resource innovation at Reykjavik Energy. She has a strong background in chemical engineering, and her expertise includes valorization of geothermal waters, lithium extraction, and geothermal resource development. She's also involved in leading the latest IDDP or Iceland Deep Drilling project, the third one, which Reykjavik Energy is working on to make happen, hopefully in the coming years. And then last but not least, this is Loredana Torsello. She is the executive manager of COSVIC in Italy. She has an extensive experience in energy environmental planning. Her expertise also includes geothermal energy development, cluster management, and international stakeholder engagement. She's as well leading the DTE in Tuscany region district, and she supports innovation in renewable energy systems. So with no further ado, I will ask basically Hugh to start the first talk. And yeah, the mic is yours, Hugh.
Good afternoon, everyone. You hear me?
Yes.
Yeah, thank you. Good afternoon, everyone. So thank you, Amen, for nice introductions, and it's a pleasure for me to start this webinar session today. So today we have opportunity to dive into the challenge and innovative solution for Superhot geothermal wells. And these applications represent an exciting opportunity for me, and especially for sustainable energy production. But at the same time, it brings significant challenge with respect to well construction and well integrities. And in this session, I would like to focus on foam cement as a critical solution for mitigating the thermal stress, for further ensuring well integrities in these applications. So let's explore together how this advancement can drive the geothermal technology further. Okay. Okay. Here, a short outline of my presentation today. So I would like to start with a short introduction to geothermal energy for those who are not familiar with that, and some unique potential with respect to high temperature energy. And then we would like to explore together the challenge posed by high temperature applications and discuss the foam cement solution as a possible reliable solution for these applications. And I would like to share with you some insight from recent R&D efforts aimed to ensure the well integrities. And finally, I would like to wrap up with some key takeaways and future perspective. As most of you may know, that geothermal energy is very reliable and sustainable power sources that we can harness from inside the earth. And it offers some very continuous energy production, regardless of external factors like weather. And the versatility of geothermal energy allows us to use it for not only for heating, cooling, but also for electricity production and even for energy storage. What is interesting with this technology is that even small amount of energy from the earth could meet the whole world's need for energy, and it makes that type of energy very interesting and essential player in our future mixed sustainable development. And why we are focusing on high temperature application in this project here, simply put, we know that the deeper we go, the hotter it gets, and the higher energy output we can have. Many studies have shown that just only 3 wells at high temperature, like 400 Celsius, can produce more or less the same energy than 42 wells at 200 Celsius. It makes the high temperature application not only low footprint, but also economically attractive. But as you know, that with high gains come high risk as usual, right? And particularly for the well integrity that we have in this application when the whole wells are exposed to high temperature. In this figure here, maybe I can switch this pointer option. In this figure here, you can see this is typical construction of geothermal wells. It consists of different layer of metal casing and cement sheets behind that. Is this construction here is different from oil and gas when completion, in the sense that the casing is cemented from casing through to the surface. And we have a slotted liner under the production casing into the production zones. And operating at high temperature conditions introduces a unique challenge for well integrity, because we have temperature cycling, high temperature introducing thermal stress and leading to a lot of thermal suspension, leading to high thermal stress in the casing and cements. And we have a nasty chemistry produce a fluid, including this hydrogen chlorides, and this is very detrimental for casings and leading to serious problems related to corrosion and scaling that we have seen in many wells in the past. In addition, we need to do the proper cementing job of the casing, especially when need to cement from the casing through to the surface. It is extremely challenging because when we are talking, this is a long depth of the wells, as deep as 5 kilometers, and cementing that long distance is not that easy. This is once a time job. If we fail in cementing jobs, we may fail the whole well construction and we lose the well. And the lack of design standard operating at beyond 300 Celsius is adding the complex problems to a next levels. So addressing all of this issue are very crucial and important for developing reliable thermal operation in the future. And a lot of data from the previous project have shown the severity of a casing integrity challenge. For instance, this figure shows an example of Icelandic case. More than 50% of investigated production wells, as you see here, are reported with casing failure in one way or in others. You may see the casing corrosion, tension stress failure, casing collapse. And it shows the need for more robust solution to withstand these thermal harsh conditions in these wells, not only for super hot application, but also for conventional high temperature application that we see here in this report. Let's have a deeper look into the effect of thermal stress on the casing material here. As you see, this is when we are subjected this material to high temperature change. The material, like a casing, experience a lot of thermal expansion and contractions. And if this thermal deformation is constrained, as in the wells, the thermal stress is going to be developed in the casing systems. And the materials, casing material, like we use here the K55 or L80, we have a specific elastic limit, and beyond which limits the casing material will develop and deform plastically. It means that we have a permanent deformations. And innovative solutions are needed to reduce thermal stress and bring the thermal stress in the casing system in the accepted level, like elastic limit here, when we are operating that at high temperature. And the reduced stress will ensure long-term well integrity. To address all of these challenges in an effective way, we need to have a deep understanding of downhole physics in this application. And at SINTEF, we develop advanced simulation tool for high temperature well analysis, which allow us to explore the use of different materials, like advanced material for casing and cements, explore the use of advanced solutions like flexible couplings, and develop alternative when design constructions to enhance performance and reliability. As you see here, an example in this figure here is the when constructions that we evaluate the potential to incorporate the flexible couplings developed by EHLA into the when construction, when design, in order to mitigate the thermal stress. As you see here, the flexible couplings was developed by our partner EHLA. It represents a breakthrough technology addressing the thermal expansions. It was developed mainly in this Horizon 2020 2020 project, GeoWells, and these couplings allows the casing segment to move in axial directions in order to reduce thermal stress and minimize the risk for failure, like casing tension and collapse. And this coupling can be designed to operate at high temperature, about 300 Celsius or even higher. And we believe that this technology is a game changer for future geothermal well integrity as a whole. And let's have a look at how this flexible coupling works. As you see here, this flexible coupling, when we are heating up the casing, the flexible coupling absorb the thermal expansions, allow the casing to move in nice axial direction, and absorb the thermal expansion in these directions, meaning keeping the axial stress in the acceptable level, and prevent the plastic formation in the casing system as a whole. And this ensures the casing system remain intact during the temperature fluctuations, making it a very attractive solution for future application. Okay, and move forward. Okay. And another key innovation that we're investigating here in this project is a flexible foam cement. The core idea is that we would like to increase the flexibility of the casing system as a whole, not only in axial directions by flexible couplings, but we would like to increase also the flexibility in radial directions. So the foam cement is, as you notice, is more compressible, and we believe that it can work hand in hand with flexible couplings in order to enhance the flexibility of casing system as a whole, and then we can reduce thermal stress. This is the principle behind this core concept. And the foam cement, as you see, this is made up by properly combining three elements: cement slurry, foaming agents, and gas as a nitrogen. When we're injecting the nitrogen gas into the cement slurry with sufficient energy, like inner pressure, we create a gas cell, and the gas will be stabilized in a small cell within the slurry, creating a lot of bubbles and porosities, increasing the flexibility of a whole system of the foam cement. In comparison to conventional cements, we see that the foam cement offer the low density. It means the lightweight, minimizing the risk of loss of circulation. We have a low young modulus to increase the flexibility, but at the same time we have a high ductility and high compressibility. It means that we have a lower risk of cement fracture and lower risk of microannualized creations. The only drawback is that this is quite a new solution, so the testing facilities is still not optimal yet. So we still do a lot of work to qualify and developing these solutions. And here you see this is the proper design of foam quality is very crucial to ensure this stability and optimal cement density, cement lightweight for successful cement job, and also to ensure the mechanical properties of foam cement for sufficient load-bearing capacity when cement is hardened and set. In this table, you can see this the influence of the different foam quality on the cement density, also mechanical properties like a young modulus, compressive strength and tensile strength of cement. As the foam quality is increasing, we are reducing the density of cement, offering this is lightweight of solutions, but at the same time we are reducing the mechanical properties of the cements. So the choice of the foam quality and solution need to be compromised and to be optimized for different applications. And in this figure, I would like to show the effect of foam quality on this well integrity in terms of the thermal stress in the production casings. As you see here, this is on the in the dot line here. This is showing the thermal stress of the production casing when we are heating up to the temperature 450 Celsius. in the configuration that we are using the foam cement to cement the production casing here. As you can see that when we are increasing the foam cement to increase the flexibility, we managed to reduce thermal stress in the production casing into the acceptance level within the acceptance limit defined by API curve, and minimizing the risk for plasticity. In some cases, we see this is still the risk for casing collapse defined by API curve, yellow curve here, orange curve here. But still, this is showing the potential and promising application of this solution to ensure the well integrity of the casings. But we can also, think of a situation to use that foam cement into different configuration. As we see here, this is for double production casing concept. When we are using the foam cement in combination with the conventional cements, we managed to bring down the thermal stress in the casings into the acceptance level, and also ensuring the well integrity not only in the buckling plasticity but also in the collapse level. The only challenge, we have a lot of challenge, of course, but the main challenge here is the cement placement of this foam cement, and a proper cement. As you have seen, this is very critical for well integrity. Especially now we are working with advanced material like foam cement, so we need to minimize the low circulations. We need to ensure that the chemical stabilize in the cement slurry when we are combining cement solution with retarder additive, refractant additive, and also gas to introduce the foam cement. We need to do proper cementing job in order to minimize the water pocket that can be created behind the casing systems. So to optimizing the placements of the cement solutions using advanced materials, this is very critical and require innovative methods such as reverse circulation that we would like to investigate it in this project for foam cement. This reverse circulation is, as you see here, we are pumping this foam cement into annulus instead for pumping the cement into the casing and circulating the cement up to the surface through the through annulus, as we have seen in conventional cementing. And ensuring the foam cement integrity requires extensive R&D activities at SINTEF and QueryStack, and through this collaboration in these projects, we are developing advanced models like a cement circulation software in order to optimizing the cementing job and the foam quality. As you see here, an example of cementing job simulation for the conventional cement placement. Also, we are successfully applied this is software to simulate this reverse cementing placement. And the software is developed by QueryStack, our partners. Is very essential to optimize the foam quality, and also this is the injection pressure during the cementing job. QueryStack is also developed a cement hydration model for foam cements in order to analyze the effect of cement hydration on this on mechanical strengths after cement displacement and also cement setting. And at SINTEF, I would like to show again these figures. We have been developing this simulation tool to analyze its mechanical strengths and also the well integrity of the system as a whole. We can analyze that effect of different cement solutions on well integrity, and also to look at how temperature and pressure change affect on well integrity as cement fracture or not, and how microannulus may be created between the casing and cement system.
Okay. Yeah, sorry to interrupt you. You have 1 more minute to go.
Okay.
1.5 max.
Thank you, Amens. So I will try to be quick here. And last but not least, you can see this is we need to ensure the good thickening time for cementing job, and SINTEF we are aiming to develop this cement retarder solution that working at high temperature applications for us to have a significant time to ensure the good cementing job here. Yeah, just a quick short overview of this, but I will jump into this one to mention that this testing is crucial for understanding how cement behave under these extreme conditions. As you have seen here, this is an example from cement integrity testing that we have done in SINTEF, and experimental results show that we have shown here this gradient crack formations under pressure and temperature change is very important for us to optimize the materials to close the knowledge gap in this development of new material solution here. To wrap up, I would like to mention this high temperature geothermal wellness offer immense potential, but we have seen this is a significant challenge with respect to well integrity. So cement as a primary barrier for casing has critical role to ensure well integrity as a whole. So we need to ensure a proper cementing design with high quality of cementing job is very important. So foam cement in combination with flexible couplings are very promising solutions to mitigate thermal stress in the future. And we still need a continuous R&D activity and testing to bridge the knowledge gap and apply this innovation to other applications in the future. Okay, by that, I would like to close my presentation and thank you for your attention. So I look forward to the Q&A session if you have any.
Thank you very much, Hugh. Thank you for the insights on these cement solutions. I think there are many questions, I'm sure, from the audience, and we will open the discussion at the end of the webinar. So just prepare them, and then you can either voice them through your microphones or just drop them like in the chat box, and we will address them. So over to you now, Tom. You can start sharing your presentation.
Thank you. Start sharing. Hi everyone, I hope you can hear me okay. It's a nice sunny day today in Sheffield, Rotherham, so it's just nice to do. So I'll be presenting on high-speed laser cladding, the benefits of that technology, going over a general overview of the technology and the achievements we've made so far within the Compass project. So TDBI's role within the Compass project was to create clad corrosion-resistant alloys onto the surface of the lining pipes that are used within geothermal environments. So the pipe you can see on the right has been heavily corroded. It's been in situ in a geothermal well. Now, I don't believe this was in for a long period of time, and there's something like, I believe, a few hundred meters of the pipe missing from the bottom. So the corrosion was that severe that it resulted in either a complete break or the complete corrosion of a large piece of metal. So TDBI's role within the project was to use high corrosion resistant alloys, or CRAs, such as stainless steel and nickel superalloys, to create a effective corrosion resistant layer on top of the mild steel substrates that's used in oil and gas industry and very widely used in geothermal environments. So within this project, we're cladding stainless steel 316 and Inconel 625 onto a K55 or J55 substrate material. So for utilizing for this project, we've chose to utilize extreme high-speed laser application, or EHLA. So this is able to deposit thin, accurate layers with low dilution and at very high speeds compared to conventional laser cladding. And one of the work packages within this project is to look at and do a study and report on the cost-saving mechanisms for extreme high-speed laser application as opposed to conventional laser application. So I'll go over very briefly the differences between EHLA and laser cladding. So laser cladding, there's a schematic it's on my left here anyway. I don't know if this is flipped for you guys. So on my left here, if you can see my cursor, laser cladding. So we have a fairly large dilution zone with laser cladding because the melting is happening on the substrate. The melting of the powder, which is being fed in here. So this is the powder being fed in here. Melting's happening on the substrate. So we get a really large dilution zone. We get a large heat affected zone. So what that does is it brings up, in the melting process, it brings up iron that's in the substrate through the deposit. So in turn, what you have to do is do more layers, so you're not getting iron coming through the substrate. Whereas with EHLA, where the melting is happening above the substrate. So the melting of the molten powder is happening just above the substrate and then is being sprayed onto the substrate, almost similar to thermal spray. So it's a buffer between thermal spray and laser cladding. So it's got a metallurgical bond like laser cladding, but it's also kind of been sprayed like thermal spray. So we end up with a much smaller heat effect zone and dilution layer, basically. So what we can do with this, we can create high precision layers from anything from 20 micron up to even 300 to 500 micron layers. We get very low heat input as an advantage. Low surface roughness, which is definitely a benefit for crevice porosity, crevice corrosion, and a high deposition rate and high speed, so we can go up to 500 meters a minute with the EHLA technology. So this is just a small video of in-flight of the melting process. So you can see the nozzle above, powder's being fed into a central position. Laser beam is hitting it. In this case, it's not fully melting it. It's just sintering the powder and then depositing it onto the substrate. But it's a very good video just to show in flight what is happening for definition of EHLA. This is another small video just to show and highlight the speed that we can process at with extreme high-speed laser application. So the technology at the moment is used in several other industries, so in valves and seats, hydraulic cylinders, brake discs, and corrosion-resistant alloys. So the technology is predominantly used as a thermal spray alternative, chromium plating replacement, weld overlay replacement in the use for application of corrosion-resistant applications. So I'll be going into now the work that we've done so far within the Compass project. So within the Compass project, we were able to purchase a large-scale machine, and I'll be going on to that briefly. But before we went onto this large-scale machine, we did some small-scale trials on a machine that was currently within our workshop. So we'd set up a nozzle for doing the external deposition at first to ensure that we were able to deposit the material onto the substrate material. We didn't get any cracking and we didn't get any porosity. So we wanted to do it in a step-by-step method to ensure we were getting the desired results. So the setup was complete here on the small scale machine. And then we did first initial trials on internal bore cladding on the small machine. Got a small video here now, hopefully it's not too loud. So this, you can just see the edge of the processing happening here. So that was on the small scale machine, and this was done within the first year of the project, just to kind of to understand how feasible is what we're trying to do. We had some issues with powder buildup as we were processing at fairly low speeds, because we only had a small machine and we only had a small amount of laser power. So these were the initial test series that we completed within the project, and some initial results. You can witness within this slide, there's quite a few defects within the deposit. So the substrate has a small amount of defects, but these defects are not desirable at all. Fairly large, so we're talking around 10 micron defects here. This is not something we want for when we're exposing a clad to when we're exposing a clad to a corrosion-heavy environment. So these parameters were refined further on the large-scale machine, and I'll share those later on in the presentation. So within the project, we aim to deliver, like Amel was saying earlier, the UK's largest extreme high-speed laser application system. So that's now been installed, but this is a brief sketch of what we were trying to do. So we were able to do work pieces up to 1,000 kilograms and length of pipes up to 4 meters with a 6-axis robot with a 2.55 meter reach and other axes as well. So it's a 6-axis robot, a manipulator on here, so 7, 8, 9. So it's a 9-axis machine we're working on. And then gantry rail at the back, so a 10-axis system. So within the project, we were able to go to the Netherlands. So that's Hornet Laser Cladding. You can see their logo up here. So Hornet are within the project as well, and we've worked really closely with them and had a great collaboration with them throughout the project. We were able to complete the factory acceptance tests with them. So you can see the cladding here. I'll just play this video briefly and I will turn the sound down. So cladding is taking place here. This is just at slow speed. So this is conventional speeds. And then we went on to trial for high-speed laser cladding as well within this project. The site acceptance tests were completed at TWI Sheffield last summer, just in late summer. So you can see up close the internal bore cladding head and the cell all set up. So we went from CAD model from small scale machine to CAD model to delivery of the new cell, which was all done under the Compass project, and a real great achievement for the project. So following that, we had a methodology of what we wanted to do for the trials. So we wanted to have a fixed spot size of 3 millimeters, because this is predetermined by the internal bore. Clad speed we wanted to keep at around a 10 meter per minute for the samples that will be tested. This is because the samples that are tested are not on a shaft, they're on either a plate or discs. So this needs to be done on the robotic arm. The robotic arms can't move at much greater speed than 10 meters a minute with extreme accuracy. So we had to do a fixed speed of around 10 meters a minute. What we did look at, though, to be similar towards the shafts is varying powder feed rate and laser power measured in kilowatts and pitch in overlap percentage. So we wanted to try and deposit as fast as possible so we could understand that we're working towards the end deliverable of understanding the economical benefits of utilizing extreme high-speed laser application. So for this, we completed a large full factorial parameter test series. So 28 samples for the first material, which was Inconel 625, and we're currently underway with doing the second material, which is stainless steel 316L. Some of the initial trials that we completed, you can see the surface roughness. So this is samples 1 to 9 of the 28 that we completed. You can see that there's a good level of surface finish for the Inconel 625 samples that were printed here. This is just a small selected and look at some of the results that we got from this test series. So we did a full analysis of all of the samples and SEM analysis for a selected few samples. So again, some small defects on these, and the thickness is not as expected on these, but this is more where we were looking at. So the defects are very, very minimal. We're getting around to 10 micron defects on these samples, and the thickness is quite desirable. So we're getting a 250 micron layer thickness, which is really what we're trying to achieve. And as I stated before, one of the main benefits of EHLA is the heat affected zone and the dilution of the weld. If this was a traditional laser cladding deposit, we'd have quite a mixing of the melt pool. So we'd have quite a lot of the substrate dragging through into the deposit. And then what that's doing is it's dragging the iron that's in the substrate, which is obviously susceptible to corrosion. It's dragging that through the deposit, and then making it less less corrosion resistant. Apologies. So from the samples, we've then ranked all of those samples, giving a layer thickness and also a score on porosity. So they porosity measurements aren't in this slide deck, but we've done a porosity measurement as well, and we've thresholded that and mapped that out as well along with this to choose the best parameter set that we'll go forward with for testing. So the findings were we've chose our best sample based on our parameters, and now stainless steel 316L samples are currently being analysed. So we've done a deposit and a test series again on the I think that's 316 samples, and they're currently being analysed as well. So following this is not my forte. I'm a deposition engineer, and one of my colleagues, Irfan, who's working on the project, is in charge of and running the testing. So this is a schematic of the autoclave that we'll be testing the samples in. So from my understanding, I believe it's a 30-day autoclave test that we're going for under conditions that have been specified by the University of Iceland and on power. That will also be subjecting the samples to a 4-point bend test to universal standards and UK standards. So it's been quite tricky sometimes getting the correct samples for the bend tests, considering the distortion and the standards. So considering the standards, samples have to be of a certain size, basically, and not on a shaft. So it's been quite difficult and challenging, and it's been really good to find it out from this project, how we need to design samples to then be tested. So it's been a real interesting project to work on. Thank you very much. That's all the slides for me, and I think I should have stuck to the time fairly well with that, Mel.
Yeah, perfectly. Thank you, Tom.
Okay.
So we are right about in time for a 5-minute break, so to hydrate, but also to use it as a time to drop down your questions, and we will come back in in exactly 5 minutes. So yeah, and then we will continue with the second session. So see you guys in a bit. So hi again, everyone. We shall continue now with the second session, and I will ask Arna Paulsdottir to come forward and share her presentation. Arna, are you there?
Yes, hi. I'm working on sharing here. See? All right, do you see my slides?
Yes, it looks perfect. So,
Great.
Mike, over to you.
All right, so hi everyone. My name is Arna Paulsdottir. I'm the head of resource innovation at Orkuveitan or Reykjavík Energy, which is leading this project. So, and I'm going to tell you a little bit about the Superhot Geothermal roadmap for Reykjavík Energy, and then about circular by design concepts in geothermal and how we've so far been approaching that that concept in this in the Compass project. And there will be a I think a report on circular by design concepts as a part of the Compass project sometime in the fall. So a quick overview of Orkuveitan first. So Orkuveitan is a publicly owned company which operates through its subsidiaries mostly. So we have a subsidiary called On Power, which operates 2 geothermal power plants and a small hydropower plant also actually. So we're operating in Hellisheiði and Nesjavellir. Hellisheiði is one of the largest geothermal power plants in the world, with an installed capacity of 303 megawatts electric and 200 megawatts thermal. Nesjavellir, which is our older power plant, has an installed capacity of 120 megawatts electric and then 340 megawatts thermal. And in both of these locations, we have seen fingerprints, if you will, of Superhot. in our geothermal fields. Then we also have another subsidiary that has to do with geothermal, and that's Veitur. That's our utility company. They operate the district heating system, water distribution system, electricity distribution system, and sewage system in a number of communities around the western part of Iceland. But yeah, most notably operate 13 different district heating systems and over 10,000 kilometers of pipes. And the largest district heating system that they operate takes about 5,500 liters per second of 84 degrees C hot water during peak capacity in the wintertime. That's about 1 gigawatt thermal, and about 60% of that water comes from the power plants. But now moving on to Superhot Geothermal. Why are we looking at Superhot Geothermal? So Superhot Geothermal has been defined in a number of different ways. The original goal of the IDDP, or Iceland Deep Drilling Project, that kind of has sparked a lot of the Superhot efforts in Iceland, at least. The original goal of that project was to reach supercritical conditions in the deep well that was to be drilled. And that means going beyond the critical point of water, so above 374 degrees C and 220 bar. We have also, at least internally, be thinking about Superhot as temperatures above 400 degrees C at depths of 2 to 5 kilometers. But really, if we boil it down to what we're actually looking for, is we're looking for enthalpy, high enthalpy in the wells, above 2,800 kilojoules per kilogram at a depth of 2 to 5 kilometers. And the idea there is higher enthalpy wells give us increased efficiency in our energy generation, but also just more megawatts per well. And that leads, hopefully, to lower costs per megawatt hour. So lowering of the LCOE. Fewer wells and more power is really what we're looking for. And to do that, we need this high enthalpy. So a brief overview of how we, of the systems that we operate in. So this is a depiction of a traditional geothermal system in the Icelandic rift zone. So we have precipitation that falls on the ground. It travels down into the ground, meets some sort of a heat source, most likely magma, and heats up, rises to the surface, makes surface or geothermal surface manifestations. That's how we know where the geothermal field is traditionally, and that's where we drill, and that's where we are operating in EHLA. So this is conventional production. But what we know is that below our systems, we have a whole lot of hot rock. We have a huge volume of rock that we're not using. So the purpose of this Superhot utilization is twofold. It's this this increase or lowered cost of energy production, and the increased production of power from each well, but it's also unlocking the rock below our conventional production zone to unlock more resources. But there's a lot of challenges when we look at Superhot geothermal. So firstly, the challenge is locating the heat source. And that, fortunately, is something that we have worked on through the years. And we have a lot of experience in these areas that we operate in. And we believe we have a pretty good idea of a number of locations where we can locate these Superhot geothermal resources. Once we have drilled and found that resource, there are reservoir characteristics that are a challenge. So what's the volume of the resource that we actually reach with the wells that we drill? And what's the permeability? Are we actually going to produce fluids from this? And then another challenge is the fluid characteristics. And this is something that we know from IDDP 1, where where there was flow from that well. But the flow was of highly corrosive fluids. So HCl is a challenge that comes with these Superhot fluids. And we've gone through some extensive geochemistry analysis to show that that's something that's going to be a problem or that's we're always going to encounter HCl there. That's just the geochemistry of the interaction of the fluids and the rocks at these temperatures that we're aiming for. Scaling is also an issue, but that's highly pressure dependent. And then another challenge is drilling deeper and into hotter formations. How are we going to do that? And then we come to what we're really doing in the Compass project, which is the well design, materials for casing and cementing. And the Compass project is really focusing on how we're going to solve the challenges in casing and cementing, as you've seen in the previous two presentations. Then there's also challenges with the surface equipment. The surface equipment being designed in a way to actually deal with these highly corrosive fluids and scaling. And then that's the utilization of the superhot fluid with the high efficiency, because we get these fluids out of the ground that are corrosive and have silica in it that's going to scale. That presents challenges in the actual operation of equipment, and we need to be able to scrub the fluid that we're getting out in a way that we're not gonna just bring it down to being like a normal geothermal fluid that we traditionally work with, and actually getting a higher efficiency out of fluid that we take out of the ground. And lastly, on before I move into the circularity, this is sort of the roadmap that we have for the geothermal or deep geothermal utilization at the Reykjavik Energy. So we're taking a stepwise approach in this. The first project that we're going to do, and one of the reasons that we're doing that first is also to sort of wait for the results from the Compass project and be able to implement those in traditional wells before we move on to deeper wells. But the first project, which is on our plans in 2026, is deep injection. So drilling an injection well that's cased and goes below our traditional production zone and into super hot formations there. And using that to support our current production. So that's 2026 in our current plants at least. And then we have the deep producer, IDDP3. That's in our plans in around 2028. And that's this traditional concept of just drilling a deep well, casing off the traditional or conventional production zone, and producing from that well. And that's where we need all of that technology that we're developing here in the Compass project. And then if we look a little bit further into the future, we are also looking at deep EGS and or what's also these days being called Superhot Dry Rock, or SHR. And that's kind of combining the deep injection and the deep production, but allowing us to move into areas where we might not have the permeability and the availability of fluid that we have in our current areas. So the roadmap that we have is we are working our way towards deeper utilization with deep injection, deep production, and then deep EGS or SHR, and then hopefully having this not just be one well of each type, but having this be a commercial thing that we can do. And as we move forward through each of these projects, we will gain experience. And there are a number of obstacles along the way. A lot of them we know about right now, and we're trying to tackle many of them in the Compass project. But we're very aware of the fact that there will be other obstacles ahead that we just don't know that we're going to hit at this point. And it'll just be a fun project to deal with those as they arise. Now, moving on to circularity and circular by design. So one of the definitions or one of the sort of scopes for circular by design is to reuse, minimize waste, recycle, and be sustainable in operations. Now, in geothermal and the way we've been talking about this within the Compass project so far, but of course our work on this is not done, as we've not turned in a report on this, is that we have two main ways to look at circular by design in geothermal. There's the circularity of the equipment that we use, but then there's also the circularity of the resource. And if we look at the equipment, a way to be circular in equipment is to have modular surface equipment. So for example, reusing silencers, reusing well houses, reusing pipes, anything that you can reuse, reuse that. So that's sort of this reuse part. Then having any equipment be made of recyclable materials. That's quite an easy thing to do in general. In general, and geothermal, we're mostly working with metals and cements, so reusable materials. This is on the surface. It is really hard to enforce circularity for subsurface equipment, as firstly, we have a really long lifetime of the wells, and secondly, it is quite a challenge to retrieve the subsurface equipment after the lifetime of the well is done. But what we can do there is, again, use recyclable materials, and that's really not something that we have to, there's not really anything that we have to change in our operations for that. But when we think about super hot utilization, that definitely comes with challenges to think about circularity, because up until now, at least, these super hot wells have been one of a kind. So the equipment is kind of being designed on the go and very bespoke for these wells. But it's definitely something that we need to think about as we want to move towards drilling more and more super hot wells to try to maintain this idea of circularity in the reuse of surface equipment. Now moving on to the resource, a way to be circular in the use of the resource is to, or my favorite way to think about this at least, is to have multiple uses of a well through its lifetime. And I'd say that's the key aspect in circular by design in geothermal, because we're not working with consumables that can be reused or recycled at the end of lifetime. We are rather thinking about the circularity in the use of the resource. And when we look at super hot wells, and you know, any geothermal well or any high temperature geothermal well, what we know is that as we start to use the resource, as we drill into the ground, drill into this overpressurized chamber that we're, or overpressurized geothermal field that we're working in, the pressure will start to drop. And you know, we can do all sorts of injection and many things to try to make sure that the power production from those wells lasts for as long as possible, but eventually the pressure will start to drop. So at the start of the lifetime of a super hot geothermal well, we can produce power from it, of course, and that's maybe the main goal when we're looking at super hot wells, is to produce power. We can take the fluid that has been used for power production and produce heat from it, thermal energy for district heating or industry. And then we can take the heat or take the fluid that comes from the heat production and use that for fish farming, for drying, for bathing, algae growing. There's lots of different options for carbon capture, like we do at our power plants. So there's lots of different options for the cascaded use of the resources, and this really hits on the sustainability part of circularity by design. So this is sort of the start of the lifetime of the well. Then as the pressure in the well drops, it can eventually drop so low that we're not getting a free flow of fluid from the well anymore. What we can do then is put pumps into the wells and still produce power, heat, and all those cascaded potential, all that cascaded potential in farming and bathing. And but eventually we know that the pressure and the temperature and the resource will drop far enough down that we will no longer be producing power from that well. So it'll be heat and other products. And then once we have exhausted the use of that well for energy production, we could use that well for thermal storage. And even also, once we've done thermal storage, we can use that well for injection. So this is really the frame of circularity in the geothermal industry, is using the infrastructure, the wells that we put so much energy and money into locating and drilling and utilizing, using that as long as possible. And then at the start of this process, when we're actually drilling the well, we need to make sure that we're putting sustainable materials into the construction of the well, and making sure that the well is constructed well enough so that it can last for a really, really long time, and can support all these different types of uses of the geothermal resource. So yeah, that's all I had today. So I'll hand it over to you, Amel.
Thank you so much, Etna. I was gonna interrupt you and telling you that you had 1 more minute, but
yeah,
that was
right on time.
Yes, perfect. So thank you so much. This was very contextualizing for why we're doing what we're doing in Compass, and all the possibilities and opportunities, but also many barriers. I think sustainability is a fundamental aspect to think about in such projects. And yeah, looking forward for the impact, like in the future, especially for the IDDP3. Yeah, moving on now to our last talk of this webinar, and it will be done by Loredana Torcello from Cosvik. So part of Compass is also, we focused on 2 locations geographically. So we have Iceland and Italy as case studies, and Loredana is going to talk today about the Italian case and how we are tackling the social aspects in terms of developing high enthalpy superhot geothermal projects. So over to you, Loredana. You can start sharing your presentation.
Okay, thank you, Amel. Good afternoon, everybody. And I'm going to share my presentation. Can you see it?
Yes.
Okay. So I'm going to present some contribution for the discussion about the tools and the approaches that we can propose to improve the acceptance of geothermal energy and the geothermal projects, since it's important that we increase the capacity of the countries, the regions, and the systems, the energetic system, to host for new plans and new projects, improving the contribution from geothermal energy to the energy transition. So the general framework, maybe you will know that because we know that geothermal energy can play an important role in energy transition. It is really rooted to the territories in which it's present and valued, and in the region when geothermal energy is present and the potential is already under exploitation, we know that the territories themselves change in alliance with the geothermal uses that we can conceive and we can realize. Further, we know that geothermal energy can support different kind of uses, can involve different kinds and different groups of stakeholders, from companies, businesses, but even for the communities and the citizens that can use and can improve the quality of life because of geothermal energy. From the energy point of view, my colleagues, the speakers that we heard this afternoon, explain quite well which is the opportunities and the characteristic of renewable renewability of geothermal energy, but we know even that it's very interesting because it is highly flexible and programmable, and so this means that the contribution to the energetic system and to energy transition can be very precious from this point of view in the portfolio of renewable sources that we can use in a region or in systems. So it's important that the characteristics are well known. We should increase the awareness about the capacity and the potential of geothermal energy, even in a cascade approach, because the industrial symbiosis that the geothermal energy can support can be the key to include the geothermal exploitation in any link of the value chain and in the life of people living near the plants. Which are the challenges? As far from our point of view, we know that there are some misperception of the opportunities and capacities and the advantages of using geothermal energy for electricity or for thermal uses, and many of these bad perception is due to the fact that the people don't know really much about these opportunities. So in our role, we know that we have to face, we are in charge with disseminate information, support the formation and the capacity building, and to explain and disseminate all the outputs coming from the projects or coming out from the research activities or the test and experimentation that we can support in order to improve the capacity of using geothermal energy and even the sustainability that is embodied in the approaches that we can support from the energetic point of view and from environmental point of view, because this is one of the main issues that we have to face in order to convince people about the capacity and the potential of geothermal energy. Maybe because of the environmental aspects and worries, most of people are skeptic about supporting new projects and the diffusion of this kind of energy sources in the market. We know that sometimes the media are not the good allies for us, because they prefer, generally speaking, to emphasize the disadvantages instead of the good and new opportunities coming up from this kind of projects or solution. And we know that we have to move in new approaches, trying to reduce the barriers and the inertia coming up from the low and poor awareness about the opportunities coming up from our proposal. The social acceptance is really important, because sometimes even a good projects for producing geothermal energy, electricity or heat can be stopped because of the acceptance is too poor. So we can face some social resistance starting from the local action groups, and the local action groups usually are able to influence the politics and the decision making. Most of the projects, can be rejected, even if the results and the benefits that we can obtain can be interesting for all the different kinds of stakeholders. We know that we have to take into account all the factors influencing the social acceptance from all the parties involved. So this means that if we have a bad perception of the impacts by the society, we know that the governance can be affected by the mood and the feeling that the communities can explain and present, and maybe can be much more skeptic about the opportunities of supporting the projects proposed by the industry. So for this reason, we have to take into account all the factors influencing the social acceptance, from the social economic conditions, the cultural approach, the geographical aspects where the projects should be located, and which are the characteristics of the subsurface and the technologies that we are going to propose. And we have to face the communication, the engagement, and the benefits in order to explain very well which are the implications of the projects and which are the way in which the stakeholders can be affected by the project itself, trying to reduce the NIMBY syndrome that most of time is one of the main problems, issues that we have to face. So in the Compass, we try to propose a working method, a methodology that is aimed to look at the previous experiences, try to understand which are the lessons to learn, and to propose a new approach or a clear approach for which the companies and the developer of geothermal projects should take into account. So from this point of view, the methodology is based on 3 different pillars. In the first one is about the 5 W. This means that we have to understand very well what, when, who, where, why a project have been to propose it. What, because we should be able to explain what we are proposing, which kind of project, and the characteristic from the design, the engineering, the technologies that we are using, when the project will be realized in the plan, who are the stakeholders from the proponents, and even from the other stakeholders that can be affected by the project themselves, where the project will be realized, of course, and why, because which are the benefits, why it's important that this project can be realized from the company point of view, of course, but even from the communities or stakeholders that can be affected more or less by the projects. To this approach have to consider which are
sounds like we all know what's going on.
Which are the boundaries of information that can be used, and we try in these months to collect all the experiences and the case studies and the best practices that we can find across Europe and across the world, trying to put together, comparing them, and obtaining then the lesson learned and the best practice to propose as different experiences. So we have to consider 2 points of view. In the communication and engaging with local communities, we collect some cases. I reported in this presentation just a few of them. Those are the projects that can be considered a successful projects from the acceptance and for the capacity of the proponents to involve, explain, and convince the communities that the project is a good thing for them in principle. So in Switzerland, in Germany, in again in Switzerland, in Lucerne. Here you can find some example in which about what are the main approaches that the proponent adopted in terms of communications activities and the results that they obtain. Even if some of these projects cannot be realized, but the problem, the issues, and the barrier in this case was not related to the acceptance, but to different kind of aspects. In case of St. Gallen, the problem was the water available and not the communities that are against the project itself. In these slides, you can find the bad experiences. In Strasbourg and in Basel, the results were completely different. The projects were stopped because of the bad acceptance about the proposal. And so maybe it's really important to understand which are the main elements that determined this kind of results.
Loredana, I have 2 minutes left.
Okay, thank you. Again, Iceland and Chile, from the analysis, the proposing benefits that they can collect. So we try to synthesize the lesson learned, the good practices from the communication point of view, the positive examples and the negative one, and from the social engagement. So this means that we should, in principle, start with a good communication, a strong communication plan from the early stage of the projects with a bottom-up approach and with a communication plan tailored to the different kinds of stakeholders and local conditions, trying to explain all the aspects, the good one and the more risky aspects of the projects without any tail cut from the information. Or the recommendation about the acceptance should start from the very beginning of the project. So this means before the exploration, up to the exploitation permits communication, which is at the end of the activities. Just a few information about Italy. This is the characteristic of the situation in Tuscany, in particular about geothermal energy systems. We have 916 megawatt of electric power plants producing about 6,000 gigawatt hours in 2020. We have 21 geothermal district heating in municipalities and some good opportunities for direct uses and cascade use of it from the power plants for dairies, brewery, greenhouses, and so on and so forth. And this is important because in this way we try to emphasize the kind of benefits that can be involved all the stakeholders, apart from the companies, the operators of geothermal plants, because this is one of the ways which we can involve and convince people about the goodness of geothermal new projects. Even from the regulatory approach at the national level and at the regional level, different laws support the importance of distribution of geothermal revenues for all the communities and for taking care about the environmental issues that can be considered under control by the population. So this is the conclusion, and to wrap up what I'm trying to say, that the perception of the geothermal project is really important, and the proper and transparent communication is a key, and projects integrated in the territories and sharing all the benefits with the population can be really important to create the condition for which new projects and plans can be realized in the next future. Thank you, everybody.
Thank you very much, Loredana. This was a great way to end this first webinar talking about the non-technical aspects as well, which matter in such complex and highly risky projects. And the case of Italy is definitely one that is worth to address, given its long history with geothermal. So we have a very short time left to actually accept questions, but we can accept 2 or 3 questions. There's one in the chat, and I will ask our speakers to come forward with me here. So we have a question from Jeffrey Garrison about laser cladding, and this is addressed to Tom. So I see like 4 questions, so I'll take the first one. Jeffrey says, how does the cost of laser cladded well casing, if using LAT, for example, compare to the cost of just using higher grade casing?
Hi guys, I'll just come in this one and go over them. So how does laser cladding affect the casing connection? Okay, good. So how does the cost of laser cladding... okay, so just using higher grades, or for a P110, I'm not sure, but I know for using a fully corrosion resistant alloy, say if we used, let's say, a Inconel 625 casing, it was something like a 95 to 97% saving. So for a P110, I still believe it'd be a substantial saving. I've not got the exact figures with me, but I have to do some I could do some quick calculations on that. But you could also as well consider the bulk cost, or the drawn cost of a P110, and then the cost of a, let's say, Inconel 625 or a stainless steel 316, and then also the amount of material that'll be cladded on. So think about it, we're trying to use a 400 micron layer. It's a super small amount of material that's being utilized in the end. Do you want to just go through the questions, Amel, or do you want to ask them and I'll respond?
Either way, you can go ahead if you want. Yeah.
Okay. How does laser cladding affect the casing connections? Do casing connections threads have to be machined differently in order to accommodate the clad? So this is a very good question, and it's not something that we're yet investigating in this project, but we did consider either a joint or cladding the thread in a thicker area, basically. So doing a clad that's thicker, and then or additively manufacturing and making the thread by a corrosion resistant alloy and then joining onto it. So the internal bore is all the corrosion resistant alloy coated, and then the thread and coupling could be made from a corrosion resistant alloy, like in 625 or a stainless steel. So the third one is also for laser cladding as well. Does laser cladding remain well bonded at high temperatures above 400 degrees C? It does. So the corrosion resistant alloy will be working around a melting point of, let's say, 1600 to 1700 for Inconel 625 and stainless steel 316L. One thing to consider is if there's lots of temperature rise and dip, because the coefficients will be different between the substrate and the cladded material. So how things expand and contract could potentially cause cracking. So it's a very interesting question. But in short, yes, laser cladding remains well bonded at higher temperatures above 400 degrees C, because it's a metallurgical bond, not just like a thermal spray where it's sprayed onto the substrate.
Okay, thank you, Tom. We have 2 more questions, one addressed to Hugh and one addressed to Artna. So the one for Hugh is, has the foam cement-based material mineralogy been checked? And what are the main difference with OPC mineralogy? So Hugh, I'm not sure if Hugh can hear us. Yes.
Hi, everyone. Yes, I'm here again. Sorry, can you repeat the question, please?
So the question says, has the foam cement-based material mineralogy been checked? And what are the main difference with OPC mineralogy?
Well, actually, basically we have not checked this minerality of this of a new solution of foam cement that we are working on. Mainly this is done by Querystack that is designing the solutions. So it's still in the phase of designing. So we'll be able to test that in a couple of months and check that mineral, and that aspect when it's coming into application and comparison with OPC So we'll come back to you as soon as possible in due course when we have more result on that. Sure.
Thank you, Hugh. So the last question is to Artna. So it says, what do you think about the new technology to drill HHR with MMW?
Yeah, I'm certainly not an expert on drilling, but I can comment on that. And MMW is millimeter wave for those who don't know that. I mean, we're certainly, if we're going to super hot dry rock, and I expect many of the people here are familiar with the plans of Clean Air Task Force to commercialize super hot dry rock all over the world, and then drilling to deeper depths than we have to do in our areas. When we're aiming for 6 to 10 kilometers, then yeah, we do need some sort of new drilling technologies. I can't really comment on whether millimeter wave or some sort of spalling or something is the way to go, but drilling is a huge component in the cost of going deeper. So I think any new technologies are welcome in that. And Amel, I don't know if you know, but there are questions also in a section called Q&A, not just in the chat.
Yeah. Okay. Let me check that. Okay, yes, there are more to you, and then a couple to Tom. So we can answer a couple here. So I can read it. I mean, have closed loop well bores been considered for these high enthalpy wells? This could potentially remove a lot of the risk associated with the chemistry of the in-situ fluids. You also don't have to figure out what to do with the produced fluids as you are recycling the same fluid over and over.
Mm-hmm.
This is from Ben Smith.
Yeah, so I mean, closed loop is an interesting avenue of research right now, and we're definitely following what's happening in Germany with EHLA loop, and how all of that goes. You tend to kind of stick with what you're used to, and we're used to this sort of geothermal operation, and it's been working quite well for us in the past decades. Closed loop comes with its own challenges. The biggest challenge, I think, is going to be the whether the is maintaining the production from the resource, as you're not extracting fluid from the ground, then you're not having this effect of heat flowing towards your well. So when you have a closed loop technology, you need to aim for this really, really, really high surface area below ground to enable continuous energy production from those wells. So I am gonna venture a guess and say that it's actually cheaper for us to produce from super hot wells and deal with the chemistry, but it's definitely an area that we're keeping a close eye on.
All right, thank you, Artna. So I will take one last question, and this is directed to Tom from Gudmundur Omar, and it says, what about differential thermal stresses of the casing material and the cladding material? Will it lead to cracking of the cladding under super hot conditions? You're muted, Tom.
Thank you. Normally this unmutes me. I kind of covered this on the last one. So
okay.
There is potential to do so, basically. So obviously there's different thermal coefficients between the clad and the substrate. So heating and cooling, there is potential to cause cracking, and it's not something we've yet investigated and seen the results of. So the question is, potentially, can it be mitigated? I would like to think so, yes.
All right, thank you, Tom. So for the record, the webinar is being recorded. It's going to be shared for all who ask about the presentations. And before we close this first event. We will have more webinars coming soon. We will dive deeper into different aspects of the project, so stay tuned. Some upcoming events we have this year. We will be present at the Italian Geothermal Forum. So Gosvik is organizing a session there. So whatever questions also you have and you have not been able to ask in terms of the social aspect and policy aspects, you can meet them there. There will be like a whole team as well from the engineering experts that you can ask there and just meet. Another event I want to draw your attention to, this is basically the summer school, Compass Summer School, that will take place in May. We will be announcing it very soon, by the end of the month, hopefully, and accepting applications for all people interested, especially the early career who are interested in engineering aspects around superhot geothermal energy, but also generally about different aspects in the project. And yes, and with that, I will thank you all for your attendance and for being here, and hopefully we'll see you again next time. So I thank our speakers too, and see you in the next webinar.
Bye, everyone.
Bye-bye.
Ciao.
Bye-bye.
Bye, everyone.